Hi, I'm Sami Sadat, and in this video, I will walk you through four real-time computer vision projects I developed during my undergrad, covering face detection, smoking detection, wildfire detection, and Hazmat sign detection. So all of these were designed for deployment on edge devices with live IP camera feeds. So my primary focus wasn't just model performance, but also making sure they ran efficiently on constrained hardware. I will go over how I achieved that using OpenCV based pipelining, model level tweaks, and intelligent resource management. So let's start with face detection. Um, so this was originally part of a larger demo project. Intended to link facial detection with national ID recognition. Due to confidentiality, I'm only showcasing the face detection portion here. So I trained a custom YOLO model, basically YOLO V. I fusioned YOLO V8 and YOLO V5 version to detect faces in real time from IP camera feeds using OpenCV. To minimize latency and prevent frame drops, I implemented parallel threading, separating video stream handling and inference execution. Beyond that, I added dynamic resolution, scaling depending on FPS, and used non-blocking input-output cues for smoother buffer management. On edge devices like Jetson Nano, this setup gave me stable throughput around 15 to 20 FPS. So this is the face detection part. So next we can go for the smoking detection project. So basically, I trained a custom dataset. This was one of the most nuanced tasks because detecting smoke, especially from something like a cigarette, involves subtle visual patterns. So I trained a custom YOLO V8 model. Here I also fusion two models, YOLO V8 and YOLO V12, with real smoking footage, and fine tuned it for cigarette smoke. For optimization, I used selective frame sampling. So for optimization, I used frames sampling and processed every third frame, and implemented a region-based activity trigger. So inference only runs if there is enough pixel intensity change in the region of interest. Additionally, I set a confidence threshold and dynamically adjusted it during low light conditions. For demonstration, I will use both a clip from YouTube and also a live prop figure to show how the system works in control and real world scenarios. So this is from the downloaded clip. So you can see it can detect when uh, basically there is a cigarette lit up, and also if the cigarette is on your mouth, it can also detect smoking. And if I go for the live video feed, so I will use a prop cigarette. I do not smoke, but um, I'll just use it for the sake of demonstration here. So it's non-smoking. Even if I'm not light up the cigarette, even if I'm not lighting up the cigarette, it's showing that I'm smoking, because basically when there is a cigarette in your mouth, it shows there's smoking. So uh, whenever it's there is smoke or not, if there is a cigarette, for basically it was for CCTV surveillance system, so it can show if there is a breach of conduct basically. So yeah, remember this was all for some bigger projects like uh, the face detection part was for a bigger portion of a project, like to detect personal information from the face, and basically detecting someone's face, and like detect basically giving output of that person's personal information. And also the smoking detection part was for CCTV surveillance system. When let's say in university premise, uh, it's, uh, it's not basically it's not permissible to smoke cigarette there. So uh, I made that project for that purpose. So let's see the next one. This is basically wildfire detection. It was done for drones and also for robots. So So this system was intended for remote surveillance towers or drones that monitor forest areas for fire outbreaks. I used YOLOv8 and also YOLOv8, basically fusion those two models, and for optimization, and also done some quantization and fine tuning in the model for speed and accuracy. So my optimizations here focused on power and storage efficiency. Basically, the input frames were resized to 480 pixel to reduce computation, and detection triggered logging was implemented here as well. Basically, only frames with valid fire detections were written to disk using CVT2 video writer. And for recorded footage, basically for recorded footage, and also if it's done in live, if it has been faded live data, in both cases I basically used batch mode inference, processing in chunks to speed up post event analysis. um, so because of the batch inference, the speed up was it basically speed up thrice. So yeah, so this is the fire detection, wildfire detection project. So I want to show another project which was basically Hazmat sign detection. Basically, the project wasn't just for detection, but for navigation safety in a larger autonomous rescue robot project. So we basically trained a YOLOv8 model, and also fine tuned it for to recognize hazardous signature like radiation, biohazard, and toxic gas warnings. When such a symbol is detected in the robot's field of view, it flags the location as unsafe for entry and update its path planning system accordingly. So it detects various kind of hazmat signs, not just only one. So to keep it responsive, I used FP16 model precision for faster inference and a basic torch.no-get pipeline. Basically, it was has to be done in a robot or local computer. So a minimal OpenCV overhead for bounding box drawing was implemented here. So basically, all of four projects were designed not only to work well in um, not only in lab inference, also let's say, so if I do the face detection here again. So basically, the projects were designed not only to work well in lab settings, but also to function in real world constraints, limited power, low memory, and live video streams, and deployment ready code. Whether it's trading for responsiveness, keeping frames for performance, or dynamic resizing and confidence tuning, these techniques allowed me to push computer vision towards real time resource efficient deployment. And so, if you're an interviewer or a collaborator and want to know more, I would be happy to show code, walkthroughs, or trade offs I made per project. So, thanks for watching. You can see all the codes in my GitHub as well. Thank you.